Hi, I'm Katherine. I'm a postdoc in Zhang's lab here at the Wistar Institute. We recently published a paper in Cell Reports that I'm really excited to discuss with you. So basically, what we study is senescence. And senescence is a growth arrest of cells. So interestingly, this was first discovered here at the Wistar Institute by Leonard Hayflick in the 1960s. And oncogene-induced senescence is a particular type of senescence that we study here in the lab. And as you can imagine from the term oncogene, this is actually very important in terms of cancer development. So when you have a mutation in this oncogene, instead of causing proliferation in cancer, as you can imagine, there's actually this paradoxical decrease in cell proliferation, which is termed oncogene-induced senescence. And this is basically your cell's own way of turning off things that might be potentially cancerous. This actually happens in humans. For instance, moles are a very good example of oncogene-induced senescence in humans. So when you go to the dermatologist, as you know, they say, this mole looks suspicious, let's take it off. Maybe later in life this would become cancerous and become an issue. So we really wanted to understand why oncogene-induced senescence occurs, how it occurs, and then how do cells overcome this growth arrest and actually become cancerous. So in our paper, we actually found that it's due to a decrease in the DNA building blocks. So if you can imagine a building that needs to be built, and there are a set number of workers, just a few workers, and a set number of bricks, and this is all very coordinated, and everyone knows what everyone else is doing, and they would build a beautiful building. But if you get activation of an oncogene, this would be like hiring 300 other builders, and they would all come in, but they're the same number of bricks, and it's very uncoordinated, and they would very quickly put something together, and they wouldn't get a building at all. Basically, they would have to stop working. And that's what oncogene-induced senescence is. So the cell no longer has enough building blocks to replicate its DNA. And so what happens then if we add back these DNA building blocks? We wanted to see whether adding back these DNA building blocks could actually lead to reversal of this cell growth arrest and potentially transformation in tumorigenesis. And that's in fact what we've shown. Now for the first time we're seeing that if we add back these DNA building blocks, we can overcome the cell growth arrest, which leads to tumorigenesis. And so in my metaphor about the building, this would be like still having those 300 workers who have no idea what each other is doing, but giving them as many bricks as they need. And so they build this very ugly, unstable building that's not going to be good at all. And that's what cancer is. I mean, basically it's just a tumor mass. It's a growth of these cells that are highly proliferative, but they're very unstable, and they get lots of other secondary hits, which is why cancer is such a complicated disease. And so we took this one step further to see whether we could take away DNA building blocks from cancer cells and whether we could force cells into senescence. And indeed, that's the case. If we take away these DNA building blocks from cancer cells, which remember have all these other mutations going on, we can senesce these cells so that they're no longer able to grow. And this could be very therapeutically relevant because a lot of times when we treat our cancer cells, we get maybe not a complete growth arrest or lots of cell death, but more of a transient cell growth arrest. And this can lead to resistance of cells and potential outgrowth of the tumor. So if we can force our tumor cells, along with chemotherapy, into a more robust cell growth arrest, perhaps we can be more therapeutically beneficial to a greater number of patients. And so basically that's what we've shown. We've shown that we know why the cells are able to go senescence because they get a decrease in DNA building blocks. And then we showed that if we increase those DNA building blocks, the cells will actually overcome this cell growth arrest and become potentially tumorigenic. And then if we take those DNA building blocks away from the cancer cells, we can force them to senesce and stably stop growing. And this is really exciting and really interesting finding that I was very proud to work on the project.